Hello, and welcome to our fourth 2020 Mighty Low Carbon Energy Center webinar, coming to you from virtual MIT, virtually all over the place in Massachusetts. I'm Robert Stoner, the Deputy Director of Mighty for Science and Technology, and I'll be your moderator today. Our intention in presenting these webinars is to cover a range of topics drawn from ongoing work in all parts of Mighty's low carbon energy centers, and a few drawn intentionally from outside them. We want you to know what we're up to at MIT and what we think is especially interesting and important as we work toward a globally decarbonized energy system. And because we want to engage and hear from you, we're presenting live, and we will reserve time at the end of this session for your questions. You can post your questions at any time in the Zoom webinar format. Just type your question after clicking Q&A at the bottom of the screen. We'll see it. As usual, we'll be recording this webinar so that you can view it at your leisure and share it with your colleagues, and we hope that you will. Wind power is a surprisingly important part of the existing global power generation mix. In the US, wind provides roughly 2.5 times as much electric energy as solar, and ranks second only to hydro. It would almost certainly be far more important still if it weren't for the fact that our best terrestrial wind resources tend to be located far from major coastal load centers. The US in particular has spectacular wind resources in the middle of the country, but they require long, expensive, and very hard to site transmission lines to deliver power to the coasts. To circumvent these challenges, there's a considerable interest in accessing near offshore wind power. Substantial technological barriers and engineering Mount Everests stand in the way. Our speaker today is Paul Slavonis, a professor of mechanical engineering and naval architecture at MIT, and the director of the Laboratory for Ship and Platform Flows. Paul is one of several faculties we've called upon to participate in the Low Carbon Energy Center for Electric Power Systems to ensure that our work is informed by experts in key low carbon generation technologies, including nuclear, geo, and biothermal power. Paul is a leading authority on the topic of offshore wind turbines, and they will be the subject of his talk today. Paul?
Thank you, Rob, and good morning, everyone. So let me go ahead and share my screen. You can see my first slide.
Yes.
Okay.
Can you go to presentation mode, Paul?
Yeah, I will go. I would like to clear my screen. And this is full screen. You can see my first slide.
Yes.
Yes?
Yes.
Okay. Let me get started. The topic of my webinar is offshore wind turbines and offshore wind energy, a renewable energy sector which has experienced significant growth over the past 10 years, which is expected to continue into the future. Wind is a vast, inexhaustible, green and low-cost source of energy, and as we will see later, it is actually very competitive with dispatchable energy sources. But before we get there, I will present and explain why offshore wind in particular is receiving the amount of attention that is receiving these days. This slide illustrates the rapid growth of the cumulative global installed wind power over the last 25 years, a growth which was nearly exponential and now is also quite rapid. And the global cumulative wind power installations are presently, this is a 2-year-old slide, but presently they're around 600 gigawatts. The question is, why has wind been so popular as a new and rapidly growing renewable energy source? And the reason is illustrated on the next slide. The reason for the popularity and the rapid growth of wind, onshore and shortly offshore, is a technology which is known as the horizontal axis three-bladed wind turbine. This is a technology which is receiving a lot of attention in the wind energy industry because it is a mature technology. It is a technology which can convert the ambient wind energy with a conversion efficiency of 50%, which is a remarkable conversion efficiency when you think that the energy that is being converted, it is converted directly into electricity. There are no intermediate conversion cycles. What's also remarkable about this technology is that the solidity ratio, in other words, the amount of area that the three blades occupy as part of the disk of the turbine is only 5%. So you need a fairly low amount of material to achieve a conversion efficiency of 50%. Moreover, there is no other technology that is anywhere close to challenge the use of the horizontal axis three-bladed wind turbine for the conversion of wind energy. I'm virtually finished teaching virtually my spring semester course at MIT, where I teach hydrofoils, propellers, wind turbines, and tidal turbines. And I keep reminding my class that the second most valuable gift of nature to humanity when it comes to fluids is lift, which is a principle that the wind turbine that you're seeing operates under. The first one, of course, being buoyancy, which is the basic principle that gave birth to the discipline of naval architecture. The largest onshore wind turbines are rated around 3 megawatts. There are some currently that are rated slightly above 3, but the reason the onshore wind turbines don't go beyond 3 to 4 megawatts is that the components of a wind turbine that's in excess of 3 megawatts in rated power are large and very difficult to transport at distant inland locations at the top of a hill and so forth. It's very difficult to transport blades that are 80 to 100 meters long, as you will see shortly, on highways. Therefore, the offshore environment is the new frontier for wind energy, which brings me to my next slide, which illustrates the cumulative installed offshore wind capacity over the past 10 years. The currently installed capacity of offshore wind turbines is around 20 gigawatts. This is about 3.3% of the global onshore wind installations. And this installed capacity is expected to reach 200 gigawatts by the end of the decade. Therefore, the offshore wind energy sector is a sector which is likely to experience rapid growth in years to come. This slide, which is courtesy of NREL, the National Renewable Energy Laboratory in Golden, Colorado, plots, I'm going to bring my cursor in, the size of the circles are the rated power, is the rated power of installed, under construction, contracted, approved, or permitted offshore wind power installations plotted on the horizontal axis. The horizontal axis plots the distance from shore of each of those circles, and the vertical axis plots the water depth where these installations are being deployed. I want to draw your attention to a couple of key points. You can see that almost all installed or planned offshore wind installations are being installed in water depths up to 50 meters. There is no circle or bullet anywhere above water depths of around 50 to 55 meters. On the other hand, their distance from shore varies from, of course, very near to shore to 150 to 200 kilometers, but it is very clear from this figure that almost all of most of the currently installed or planned capacities are in distances that are somewhere between 0 and 50 kilometers from shore. One of the limiting factors for offshore wind turbine installations is the visual impact. Whether we like it or not, people who live near coastal communities object to very large wind turbines spinning in their backyard. And here is a very simple formula, which I actually was asked to derive by a journalist 15 years ago before he was prepared to publish an article about offshore wind energy, which gives us the distance from shore beyond which a tower with height h, it becomes invisible. In other words, if you put a tower, which is 100 meters tall, typically the height of a tower of an offshore wind turbine, if you put it at a certain distance from shore given by L, and if R is the radius of Earth, 6,371 meters, turns out that if you place a tower 100 meters tall at a distance of 35 kilometers from shore, it will be invisible, assuming perfect visibility. That's about 22 miles. So the zone of visual impact of offshore wind turbines is anywhere between 15 to 20 is in practice a sufficiently large distance beyond which you would not be able to see a large utility scale offshore wind farm. This is a key figure which we will come back to later on when we talk about bottom mounted versus floating offshore wind turbines. What are the benefits of offshore wind energy? And what are the reasons why this sector is receiving so much attention? I'm going to go slowly through each line. Offshore winds are higher and more persistent. The wind turbines that the industry is manufacturing as we speak for the offshore environment are ranging from 6 to 12 megawatts. Their diameters are 160 meters up to 214 meters. The longer blade that has been manufactured to date is for the General Electric Halia 12 megawatt machine, and it has a radius of 107 meters. So the diameter of the 12 megawatt GE machine is 214 meters. That's a lot of real estate. That's a lot of area across which the turbine captures and converts wind power into electricity. The height of the towers of a 12 megawatt turbine the 12 megawatt, 10 to 12 megawatt turbines can go up to 150 meters above sea level. Turbines which have towers 150 meters tall with blades of 100 meters in radius can easily be assembled in coastal facilities and very difficult to do the same in inland facilities. An additional advantage of offshore wind energy is the capacity factors of a utility scale offshore wind farm range from 40 to 50%, and in certain cases it can exceed 50%. And we will see later on when we talk about the levelized cost of energy, the capacity factor and the size of the turbine are significant parameters which lead to a lower levelized cost of energy, and you will see how that comes about. For bottom-mounted offshore wind turbines, the technologies that have been developed so far are listed in this slide, courtesy of the Intergovernmental Panel for Climate Change. Of those 5 technologies, for water depths that are anywhere between 0 and 50 meters, the monopile is by far the most popular. This is a monopile which is driven in the seafloor for water depths up to about 30 to 40 meters. The depth of the part of the monopile under the seafloor is also around 30 to 35 meters, and everything above the water is what I just described. In water depths that are in the range of 50 to 60 meters, the jacket, which is a structure that has been widely studied by the oil and gas industry, is being preferred. And you will see an example of a jacket foundation shortly. It is being considered mostly for water depths greater or close to 50 or 60 meters, in certain cases up to 70 meters. It is a lighter structure, but it is more labor intensive, and in certain cases it is more prone to fatigue. But those are the 2 technologies that have been extensively studied for bottom-mounted offshore wind turbines. And there is some interest recently on gravity-based structures made out of concrete. In the case of the jacket and the monopile, they're almost always exclusively made out of steel. My traditional field of expertise is my marine hydrodynamics and design of ships and oil and gas platforms. About 20 years ago, I saw this picture, the one on the right. The picture on the right is the first offshore wind farm that was deployed off the coast of Denmark. Is the Horns Rev bottom-mounted offshore wind farm, which is built out of 2-megawatt Vestas machines. This is a very nice picture that shows the wakes left downstream from the front row of turbines and how the wakes interact with the turbines that are deployed downstream that you cannot see. The reason I point this out is, as a good naval architect, 20 years ago, when I first saw this picture, I immediately thought that these turbines were floating. And of course, they were not floating. They are bottom-mounted turbines that are installed in water depths based on monopiles of 20 meters or less. So the first offshore wind farm was installed in very shallow waters, and that is really what got me started in my lab over the past 20 years to look into floating wind turbines, which is a topic that I will come back to later. Another topic which is very important for the development of utility scale wind farms is the interaction of the wakes of the front turbines with the aft turbines and the efficiency loss and the energy yield reduction as a result of the shadow effect of the wakes that you see here. And the picture on the left is a recent computational fluid dynamics simulation of what the flow looks like as simulated with advanced computational fluid dynamics methods. The design of the layout of the wind turbines in a utility scale wind farm is a very interesting fluid dynamic problem because of the wake effects. And more recently, it has been observed by industry that the wind speed that the front row of wind turbines see coming in is being blocked by the rows of turbines that are behind them. So there is an interesting blockage effect that comes into play, which leads to a reduction of the energy captured by a few percent. And that reduction by the current standards of the wind energy industry, which is quite advanced, is considered significant. So there are important wake and blockage effects that the industry is looking at when they decide how to deploy a large number of offshore wind turbines in a utility scale wind farm. This is the first offshore wind farm in the United States. These are 5 turbines. You don't see the 5th one, which is out here. This is the Block Island bottom-mounted offshore wind farm. They are equipped with GE Renewable 6-megawatt turbines. This is the 6-megawatt turbine with a diameter of 160 meters. The blade radius is 80 meters. And as you can see, they are supported by a jacket, which is one of the 2 foundation technologies that I described a moment ago. The water depth is around 40 meters. And this farm is deployed off the Block Island offshore Rhode Island. In order to install offshore wind turbines on bottom-mounted foundations, we need jack-up installation vessels. Those are vessels. This is a ship or a barge, whichever way you want to look at it, which when brought offshore, it is basically jacked up. In other words, it essentially supports itself on legs. You can see 4 legs here, which are basically sitting on the seafloor. The vessel is raised. So the vessel that carries the blades and the tower and the foundation components is sitting on a solid foundation, the seafloor. And you need the vessel to be sitting on solid foundation because you need a lot of precision when the crane lifts the pieces of the turbine that are being installed offshore. So this process of transporting and installing the components of large-scale offshore wind turbines requires the construction and chartering of vessels, which are quite expensive to hire, and they contribute to a significant degree to the cost of bottom-mounted offshore wind farms. So that technology is becoming more and more important now that there exists a lot of projects that are being planned for deployment around the Northeast United States. And the cost of this technology obviously is a cost that adds itself up to the operation and maintenance cost of bottom-mounted offshore wind farms. In order to bring the cost down, the alternative would be to, instead of having bottom-mounted foundations, is to design the foundations to be floating. And that is an area that my lab has worked on over the past 20 years. What are the benefits of floating wind turbines? Obviously, floating wind turbines can be sited further offshore, and they mitigate the visual impact, which we know is there, and the noise impact, which often is a factor that contributes to coastal communities objecting seeing the farms very close to their coastal homes. If you site an offshore wind, a floating offshore wind farm 15 miles beyond the coastline, they effectively become invisible. So industry has sort of found out that 15 miles is a typical distance from shore, beyond which human eye doesn't care if they see a blip in the horizon. My simple formula said 22 miles, but in practice, anything between 15 and 20 would make a tower that's 100 meters tall effectively invisible from the coastline. Floating wind turbines can be deployed in water depths anywhere from 30 to over 200 meters. There is effectively no limit in the water depth other than the cost of deploying longer mooring lines. But otherwise, there is no effective limit on how deep the water might be when you are developing floating wind turbines. The floating wind turbine can be fully assembled at a coastal facility and can be towed out in a very low-cost manner. You don't need any jack-up installation vessels, and that brings a significant reduction in the deployment and operation and maintenance costs. Floating wind turbines, and the same thing applies for bottom-mounted wind turbines, favor to deploy large multi-megawatt wind turbines. The industry is clearly moving towards the largest possible wind turbines they can manufacture, because the marginal cost of building a larger floater is clearly much lower than the marginal cost of doubling the rated power of the wind turbine. Buoyancy is very inexpensive relative to building larger and larger wind turbines. So larger turbines on fewer floaters immediately bring lower operation and maintenance costs per megawatt. If you have a 12 megawatt turbine on a floater versus a 6 megawatt turbine, you need to take fewer trips per year per rated megawatt to maintain the turbine that is sitting on a particular floater. So those are clear benefits for floating wind turbines, and there are a lot of developments as we speak of various designs of floating wind turbine supports for future deployment. So that you can get an idea of the payload that a bottom-mounted or a floating foundation carries, this is a fairly reliable table of the weights and loads of a nominal 6 megawatt wind turbine. The numbers of various manufacturers vary. They are obviously not very forthcoming to give us detailed numbers, but these are fairly representative figures. The weight of the rotor, nacelle, and hub assembly, the RNA, is about, for a 6 megawatt machine, is 350 tons. That's at the top of the tower. The top of the tower carries 350 tons. The tower, made out of steel, is also about 350. The center of gravity of those two masses is 75 meters above sea level. So we have a structure with a fairly high center of gravity, which is an important consideration when we design these structures for stability. The typical height of the hub, in other words, the tower typically has a height of 100 meters. It can go up to 120 or even 150, but I'm working with a baseline figure, which is here 100. When the wind blows at a wind speed of 12 meters per second, a wind speed of 12 meters per second is about 24 knots, not knots in nautical terms. For a diameter for a 6 megawatt machine of 160 meters, a wind blowing at 12 meters per second is going to exert a horizontal force 100 meters above sea level of 75 tons. So we have a significant horizontal force acting by the wind 75 meters above sea level. This is the point of effort of the force from the wind on the wind turbine. That's a significant load that we have to design this offshore wind turbine for. We are designing these turbines to withstand hurricane level winds. When a hurricane comes around, hopefully it doesn't come around too often, but we know they come around quite often around the northeast of the United States. And if the wind speed of a hurricane is 40 meters per second, and we know it can be a lot higher, we park the turbine at a wind speed of around 25 meters per second. The turbine blades are parked, but the wind blowing at 40 meters per second or more, this can go up to 60 or 70 meters per second. It will exert a force, which is mostly drag on the blades and the tower, which is around 200 tons. And that load is acting around 67 meters above sea level. The point of this discussion is to illustrate how significant are the loads that these turbines are going to experience in severe weather environments and how high these loads are exerted. Therefore, when we design foundations and mooring lines and anchors, we have to take these loads carefully into account. And I'm going to spend the next 2 slides to summarize the types of loads that we have to design the structures for, which of course drive the safety of the system, but also its cost. So the offshore wind and wave environment exerts upon those turbines static and dynamic loads in hurricane winds and waves, which is what I just discussed a moment ago. When we design these structures, we have to always take into account that those are 200-meter tall, slender towers, 100 meters for the tower and 100 meters for a long blade. So we're talking about a 200-meter tall flexible tower with blades, which will, under certain environmental loads, resonate. There will be resonant flexural vibrations, and we want to make sure that we design this structure in a way that these flexural resonant vibrations are not going to cause fatigue in wind and waves that always, not always, but most of the time they come at the same time. We also have to design them to make sure that the extreme loads in hurricanes and the fatigue due to resonant flexural vibrations are not going to fatigue the structure, causing cracks. In addition to the environmental loads that we obviously have to design the structures for, another significant load occurs when you accidentally lose power from the grid. If for some reason the power of the grid came down, say there was a blackout, the farm is going to stop producing electricity, and the load, let me go back here, the load that would be exerted because the turbine would be spinning, producing electricity, 75 tons would suddenly go away. And when the load goes away, you essentially receive a negative jolt. The tower is effectively feeling a jolt of lost thrust. And that powering off is a significant load that can contribute to extreme loads and fatigue. So in order to design these structures, we have to really consider all combinations of winds, wave, powering on, powering off. And for these, we need accurate and efficient simulation tools. The industry has spent a lot of effort over the past 10 years and has borrowed a lot of expertise from the oil and gas industry that has designed oil and gas platforms in order to simulate all the environmental conditions that both require simulation tools from the wind industry for the wind turbine analysis and analogous tools from the oil and gas industry for the bottom mounted or floating foundations. Typically, we are looking at 1,000 design stages. So the analysis of these structures require a very large number of case studies, and the simulations we are carrying out need to be both accurate and efficient. So there has been a lot of effort devoted by academia and industry towards the development of accurate and efficient simulation tools. The optimal wind farm layout is a topic that I touched upon earlier. This is another important topic that requires the use of advanced computational fluid dynamic methods in order to evaluate the effects of wake shadow, shadowing, and blockage. In order to mitigate and reduce the loads that these structures experience, the wind turbine industry is borrowing tools and technologies that are widely used in tall buildings in earthquake-prone parts of the world. In order to mitigate the vibrations of a tall, slender tower, I mean, as I pointed out, we are talking about a 200-meter tall, slender tower. In order to mitigate the vibrations of this tower, we basically need to introduce what we call in structural dynamics damping. We need to introduce mechanisms that mitigate or reduce the resonant vibrations, and we have borrowed tools from the civil engineering community primarily that have been used in various shapes, forms, and sizes in very tall buildings in earthquake-prone areas. And some of these tools and technologies are tuned liquid dampers. Those are basically containers filled with water or other fluids, which have a significant mass as a percentage of the mass of the structure. Those are known as tuned liquid dampers. In addition to the tuned liquid dampers, the industry is using tuned mass dampers. Those are mass dampers made out of some heavy material that is either controlled fully or semi, or passively designed or fully controlled with power electronics. Those are not visible to the eye because they're always installed inside the structure, and those are technologies that are very effective when properly installed and designed, that the industry has looked at quite actively. When we are looking into the design of floating supports, it is important to always think about the optimal combination of the type and size of the wind turbine floater, the mooring lines that the floater is connected with to the seafloor, and the type of anchors that are employed. The optimal design of floating wind turbine concepts require the optimal selection of those three subcomponents, which is the reason why there is so much interest and research and development in the area of floating wind turbine concepts as we speak. Finally, and this is an activity that my lab at MIT has been active in over the last 5 years, in order to mitigate loads, you can now develop forecasting algorithms that draw upon machine learning technologies that allow us to forecast wind speeds and waves over short time intervals of the order of a few seconds to the order of a few minutes. And these forecasts, when properly made, can be factored into the development of controllers, which controllers control the pitch blade, the blade pitch angle to mitigate vibrations. It can be used to control the operation of dampers and so forth. So controller design can benefit a lot from the availability of forecast of wind and waves, which can actually be carried out going out a few hours if you want to forecast the electricity production of a utility scale wind farm. Okay, so I've given a fairly general presentation of the various components that, technology components that go into a bottom-mounted and floating wind turbines. I'd be happy to answer any more questions in more depth. Concluding, I would like to address now the economics of offshore wind turbines and why the industry is trending towards larger machines and why we expect the levelized cost of energy of offshore wind turbines to go down in the future. This slide basically is a summary of how we arrive at the levelized cost of energy, and in particular, what parameters, what metrics of large-scale offshore wind turbines drive the levelized cost of energy down. Let me start with some basic economics. The rate of return, or the weighted average cost of capital of any investment, is the ratio of the annual income, or the coupon from this investment, divided by the capital investment, which is CapEx. The capital investment in any real asset is going to generate an annual income. The ratio of the two is the rate of return. Moving this to the left-hand side and moving the weighted average cost of capital in the denominator, we can rewrite this as the standard formula for net present value. The capital invested, which is the net present value, is the ratio of the annual income divided by the rate of return, or the interest rate. The annual income from an offshore wind farm is the product of the levelized cost of energy, the cost at which you will be selling your megawatt hour to the market, times the annual energy production. I'm working with annual income. So annual energy production times levelized cost of energy minus operation and maintenance expenses per year. That's the net income. Income minus expenses divided by the cost of capital. 5%, 7%, that's a combination of debt and equity. The annual energy production is the number of megawatt hours that the wind farm is going to generate over a period of a year. So the capital expenditure for a large-scale offshore wind farm is the ratio of those two quantities. I'll come to the annual energy production here. When you take this equation and you rearrange it, move the levelized cost of energy, rearrange it, and a simple rearrangement of this equation gives us the formula for the levelized cost of energy is the capital expenditure times the weighted average cost of capital. Take this, multiply by this, and move this to the left-hand side and divide by AAP. So the levelized cost of energy formula, which is basically the fundamental formula that is being used to figure out cost of energy, capital expenditure, weighted average cost of capital, 5%, 7%, plus operation and maintenance per year divided by the annual energy production in megawatt hours. The annual energy production of a wind farm is the product of the capacity factor, the percentage of time the wind blows and the wind farm generates electricity. We know there is discussion, the wind doesn't blow all the time. Of course there is. The wind farm is not going to be generating electricity 24/7. It will be generating electricity by a certain percentage of the time around the year, which is contained into what we call the capacity factor. So the annual energy production is the percentage of time the wind turbine will be operating as a fraction of its rated power, times its rated power, 6 megawatts per turbine, 12 megawatts per turbine, whatever, times the number of hours per year. That's an easy figure to remember. Very easy to remember the number of hours per year, 8,760. Just go down from 8 and you will have the number of hours per year. This is the denominator. Capacity factor times rated power times 8,760. Plug this is, the acronym is CP is capacity factor, P is rated power, number of hours per year. Take this and plug it here. And this is the formula that I would like to draw your attention to. This slide explains how this formula came about. Basic economics, basic definition of annual energy production. But this formula is very revealing and points to the reason why the offshore wind energy industry is moving towards large turbines. The levelized cost of energy is going to be lower. The lower is the capital expenditure per rated power. What that means is you need a lot of megawatts per floater or per foundation. If you have a 12 megawatt machine supported by a floater, this becomes twice as small versus having a 6 megawatt machine, because the P in the denominator is the rated power per foundation. So clearly you want large turbines on foundations because, as I pointed out earlier, the marginal cost of the foundation, bottom mounted or floating, is much lower than the marginal cost of building a 12 megawatt machine versus a 6 megawatt machine. Clearly lower cost of capital, lower levelized cost of energy. The developers know very well how important it is to command a low cost of energy, a low weighted average cost of capital if the project is properly de-risked. Operation and maintenance obviously is an additive cost, but again, you want to have a large P in the denominator, because if you have a 12 megawatt turbine versus a 6 megawatt turbine on a floater, you will need to take twice as few trips per year with your boats to go out and service the farm as it needs to be serviced, say, twice a year. Large capacity factors, lower levelized cost of energy. Obviously, you want a capacity factor that is as large as possible because it appears in the denominator, and offshore wind farms because the wind is steadier and higher, will obviously have higher capacity factors, which are in the range of 45 to 55% versus onshore capacity factors, which are in the range of 35 to 40%. So this formula explains why the offshore wind energy industry is moving to as large turbines as possible on bottom-mounted or floating foundations. Concluding, this is a fairly busy table. I will draw your attention to a few figures here. This is the levelized cost of energy of electricity of new generation resources that will enter in service in 2025 in 2019 dollars per megawatt hour. This is courtesy of the U.S. Energy Information Administration. It's a recent table. Basically, what this table lists, these are dispatchable electricity generation sources, supercritical coal, combined cycle gas turbines, and so forth. Capacity factor. The capacity factor of offshore wind is 44%. Capacity factor of onshore wind, 40%. Levelized cost of electricity, $90 per megawatt hour offshore without operation and maintenance, 29 onshore. This is a proof, this is the reason why onshore wind has grown so briskly over the last 20 years. Obviously, we know that onshore wind now is very inexpensive. Operation and maintenance for onshore wind is less than offshore wind. The offshore wind operation and maintenance is about 30% of the capital cost of buying the turbines and foundations. And that is the reason why jackup vessels need to be designed and built in a way that become cost effective. Transmission costs, you can compare transmission costs per megawatt hour for dispatchable sources. And here is offshore wind, onshore. Photovoltaics, we know they are inexpensive, and the levelized cost of energy is $24 per megawatt hour. Operation and maintenance, $6 per megawatt hour. Offshore wind, everything included, presently $122 per megawatt hour, and almost everything here, I think everything here is bottom mounted. We expect this figure to come down significantly when floating supports become mature and are deployed at the utility scale. Everything included, offshore wind, $122 per megawatt hour, onshore wind, $39 per megawatt hour, photovoltaics, comparable to onshore wind, hydroelectric, more expensive than both onshore wind and photovoltaics. And you can see that onshore wind now is less expensive than combined cycle gas turbines. And that's the reason why wind is so popular as a non-dispatchable, renewable energy source. That's a very nice revealing table that shows us the current trend and the current levelized cost of energies for a wide range of electricity generation resources. And you can web search this, document, and you can download it, and you can see more details of how these figures have been arrived at. Conclusions. The reasons why offshore wind is expected to grow in the foreseeable future is the resources offshore are vast, and they're available for wind source development. Wind turbines and marine structures are mature and low-risk technologies, as opposed to other renewable energy technologies, which entail a significantly higher level of risk. Three-bladed horizontal axis machines, no matter how complex they are to build, they are now a mature technology. We understand their physical operation very well, and the same applies to the marine structures that we are looking into for floating foundations. Floating wind turbines are a key technology because visual impact is an issue that utility scale offshore wind farms have to face. And repeating what I've said a number of times, large turbines with high capacity factors and low operation and maintenance costs are the reason why the levelized cost of energy is going to become lower and lower offshore, simply because the marginal cost of floaters per rated megawatt is significantly lower than the marginal cost of building turbines in the range of 6 to 12 megawatts. That's all I had. I would be happy to take any of your questions.
Thank you very much, Paul. I just remind everyone that you can ask questions through the Q&A box at the bottom of the screen, and we'll be watching out for them. But I've got a whole bunch. While we wait.
Can you bring me back? I'm not able to.
To close that, you click on the share screen button, the green button down at the bottom, and I think it will stop.
Okay, there I am. Okay.
Yep, we're back.
Yep.
I have a floater. It's a 40-foot tartan sailboat, and my floater cost me a fortune to maintain. And I was looking at your fixed O&M costs and wondering how floater maintenance costs compare with fixed platform costs. Are they less expensive?
Well, if I was looking at the IEA offshore wind turbine cost, I presume the O&M cost for offshore turbines includes the jackup vessels. You will not need the jackup vessels for floaters. So the O&M costs for floaters are going to be a lot less than O&M costs for bottom-mounted foundations, because you will not need to account for the jackup vessel. If you don't account for, leaving the jackup vessel aside, the rest of the O&M costs are going to be comparable. You will need to go out with with little boats to move equipment, to move lubrication, to move a gearbox. So the number of trips per year, either once or twice per year, are going to be the same, because the turbines are going to be the same. They will be both in the range of 6 to 12 megawatts. So my guess, it's not a guess, you would need to basically go out as often for floaters as you would need to go out for bottom mounted, discounting, of course, the jackup vessel cost. And that's the reason why I expect the O&M costs of floaters to be a lot lower, which is one of the reasons I expect the cost of electricity to come down when floaters become commonplace.
Would it be typical to do that O&M out at sea, or to tow them into shore?
That's a good question. It depends on the design. You can conceivably, depending on the kind of mooring system that you have, you can conceivably disconnect the mooring system and tow the whole floater to shore. All of the floaters that I have seen develop so far, which are fairly advanced in development, can be towed to shore. Okay. So if they are deployed, say 30 to 50 kilometers, or say 20, 30 miles offshore, and you'd rather tow them to shore to replace the whole turbine, it may be less expensive to tow them into a port than take the turbine offshore. And that's almost certainly going to be the case if you need to replace a large piece. So that would bring down the O&M cost even more. Yeah. All of the ones that are being developed so that they can be towed to shore for major maintenance.
Questions are starting to come in online. There's one from Jesse Teichman of Chevron Ventures, asking a question very similar to one I was also thinking about, looking at these huge rotors, and asking, are novel turbine designs showing potential to reduce array spacing requirements below this 10x rotor diameter rule of thumb? In other words, can you space them closer?
Oh, space them closer.
With rotor design.
As a rule of thumb, the spacing between turbines so far has been about 7 times the diameter. So if you have a diameter, say of 100, let's say 200 meters, just to keep things round, the GE diameter is 215. If the diameter is 200 meters, we're talking about a spacing of 1,500 meters from turbine to turbine. Now, I do not know, I must admit, I do not know if there is a benefit to be gained when you bring the turbines closer to each other, say 5 times the diameter. The wake shadowing effect, every turbine leaves a wake, which means a velocity defect. So the aft turbines are going to be seeing less of a wind speed, and you can see reductions in productivity of the order of 10% or even more. There have been a lot of studies done with CFD, computational fluid dynamics, of what are the benefits of spacing them transversely and longitudinally, more or less. I do not know if there is a benefit toward bringing them closer to each other transversely or axial or longitudinally, and that's an issue that is being looked at with CFD simulations. One topic that came up which has received a lot of publicity recently is that the aft turbines, if you have 10 rows of turbines, from the second to the 10th row, the turbines from the second to the 10th row block the wind coming into the first row. And this is something that the industry had not appreciated, and they realized that their simulations and their developers were assuming that the wind that the front row sees is not being affected by the aft rows. It turns out that they are. They generate blockage. And that blockage leads to a reduction of the energy yield by a few percent. And a few percent in this industry is not insignificant. And now that's being looked at. There have been papers published a few months ago that look into the reduction of the wind speed coming in. So there is reason in the direction of the wind. I don't know if there is a benefit to bring them closer together in a direction transversely to the direction of the wind blows. But it is an important design parameter that is very closely looked at by the wind energy industry and developers.
Brad Hager asks the question that's probably on many people's minds about your last table, effectively, where you show a not very exciting current state of the art in terms of cost competitiveness with natural gas and onshore wind, something like a 3 times cost difference for offshore wind. How and on what timescale, Brad asks, is that gap going to close?
Developers who now are more familiar with the manufacturing costs of the towers, the industry has gravitated towards monopiles. By far, over 90%, 95% of the installations, perhaps more than 95%, are monopiles. And the reason they are monopiles is the industry now has developed manufacturing methodologies and pipelines that can build monopiles out of steel very inexpensively. So the trend towards monopiles is driven by cost, and the cost of steel obviously is the major commodity cost. These costs are coming down. I don't know what was the time when this table was put together, but I see from developments in the UK that the cost of offshore wind over the next 5 years with monopiles is going to come down below 100, perhaps closer to $70 per megawatt hour. You need to factor in the cost of drilling and installing the foundations and jackup vessels. But clearly the trend over the next 5 years is for less than $100 per megawatt hour. And when floaters come around, I wouldn't be surprised to see the cost coming down to the $70 to $50 range. But one other consideration that I have to really mention is I don't know if the costs that the IEA table listed were based on 3 megawatt turbines versus 6 megawatt turbines. The cost of my formula of the levelized cost of electricity clearly illustrated that when you have a large rated power in the denominator, your LCOE goes down a lot. If the table was produced with the standard offshore wind turbine, which used to be 3 megawatts, that LCOE will come down a lot, perhaps by a factor of 2, by going from 3 to 6. And if you go from 6 to 12, it may come down to even more. So a key parameter, which is the reason why I produced the formula for LCOE, a key parameter is P, the rated power. If you plug in there 12 megawatts, you may see the $120 come down to 6 or less. So that's something to pay close attention to.
So that feeds nicely into probably our last question that relates to the developing U.S. supply chain for floating versus fixed offshore wind. And I guess perhaps as an adjunct to that, if I could also ask about ongoing demonstration projects and how this industry is developing.
Well, in the U.S., the two developments that have been going on for quite a while from U.S. entities are WindFloat, which is a company founded in Berkeley, California, which developed a semi-submersible floater, which now has been built and it's no longer demonstration, but it's now being deployed off the coast of Portugal. And the other is the Voltron US demonstration project of the University of Maine. The University of Maine has been doing a lot of work over the last 10 years, and they have been funded by the Department of Energy, and they have developed also a semi-submersible floater, which has been built at the 1:8 model scale and has been deployed in the Gulf of Maine. It is a semi-submersible, fairly similar to the semi-submersible of WindFloat. And those are the two floating demonstration projects that have been developed in the United States. And they are still at a fairly early stage. They are not nearly, at least, well, WindFloat has been around for 10 years, about 10 years. But for the Northeast US market, which is a market that is attracting a lot of attention, there hasn't been any discussion that I know of that basically is addressing the deployment of utility scale wind farms with any of those two demonstration floating wind turbines. Most of the developments that are being discussed now are bottom mounted foundations because almost all of the Northeast US, all the way out to the continental shelf, has a water depth of up to 50 to 60 meters. I think the maximum goes down to 70. If you come closer to the coastlines and even beyond that 15-mile zone of visual impact, you can conceivably build economically viable large-scale utility farms with monopiles or jackets. So the industry knows that as soon as the cost of monopiles and jackets go down with the large machines with 6 to 12 megawatts, those would be the first projects to go in the water. And because the water depths are so shallow and because the wind resources are so ample, the emphasis for now is for bottom mounted. But clearly floating has advantages, which I've underscored.
So I get the impression that the particular question that Pierre is asking about the relative supply chain development may be a little premature, at least for floaters, in light of the small number.
Well, I mean, you need the ports, you need the facilities that would assemble the blades, that you would need a lot of infrastructure along the coastline, regardless of whether you go with bottom mounted or floating. The key technology that is distinct for bottom mounted is the jackup vessels. But everything else is the same. So all the infrastructure you would build for bottom mounted would be basically ready for floaters when floaters come around. The only additional technology is the jackup vessel, which is a separate vessel that needs to be built, that can be installed in water depths, whatever they might be, 30, 40, 50 meters, and would be able to install the pieces of the 6 to 12 megawatt machines. So everything else is the same. So the infrastructure that's being built now is being planned for the bottom mounted will be basically ready for floaters.
Does that mean that there's a bit of a chicken and egg problem in this industry development here, that you have to build the infrastructure in order to make these things economic, and they won't be economic until you build the infrastructure?
Well, the port infrastructure is fairly easy to build. I mean, there is no, I mean, as soon as the permitting is in place and as soon as the development is going to go ahead, The coastal infrastructure is fairly easy to build. It's just a matter of committing the resources to build the coastal infrastructure, and then you will see the wind turbine industry basically ramping up the construction of the large machines. The issue of the jackup vessel for the United States is the Jones Act. The jackup vessel, according to the Jones Act, is required to be built by a U.S. entity. The Jones Act is an act of Congress that requires that vessels that move from U.S. port to U.S. port are built by a U.S. entity. So that technology, that infrastructure is what needs to be planned ahead and built, and that is a commitment of resources that needs to comply with Jones Act. Port facilities are fairly easy to build, and they're being planned both in Massachusetts, Rhode Island, New York. Blade manufacturing facilities exist. All of the rest exist for the onshore industry. It will be ramped up for the 6 to 12 megawatt machines. So that part is gonna be fairly easy to ramp up. The Jones Act vessels are the ones that require commitment, and this commitment will become more concrete when the permitting is in place and the projects, bottom-mounted ones, are going ahead.
Fantastic. Well, thank you, Paul. This has been really a fascinating introduction to an obviously important and emerging subject, and we look forward to hearing from you again soon. Thanks for joining us, and thank you.
Pleasure. Yep.
We'll see you all again in roughly a month with our next webinar. Thank you very much.